recording. Okay, welcome everybody. Today we are going to listen Nuri, who's a PhD candidate. He's in his final year and I think in the process of almost writing his thesis at the Cognitive Systems Group at the University of Tübingen. He's interested in autonomous driving, the perception side of things, and he's going to tell us about a few of his methods that he's developed so far towards descent. And yeah, without further ado, I want to leave the floor to Nuri. And another reminder, Nuri is our postdoctoral candidate. So, we will ask your opinion about him, want your feedback after this. So keep that in mind as well. Yeah, so Nuri, the floor is yours. Okay.
Yeah, thank you everybody for giving me this opportunity to share some of my work doing my PhD. So my PhD, so my talk is going to be about instance segmentation and 3D multi-object tracking for autonomous driving. Yeah, so first, as a motivation for autonomous driving or self-driving, so the main advantage of autonomous driving is that it reduces accidents, and car accidents actually are the main reason for death for young people, especially between 5 and 29, which is a report by the World Health Organization. And the main reasons for these accidents are distraction or drinking or simply not following traffic rules, which autonomous driving could solve these problems. The second motivation for autonomous driving is providing mobility to people who cannot drive, for example, blind people, elderly, teenagers, and so on. So that could improve the quality of life for many people. Also, it could save time. So many people are going to their works and it consumes a lot of time. It would be nice if we could give them back their time. It could provide new public transportation methods. For example, car sharing, carpooling could be way more easier if cars could be programmed and so on. And there are even more crazier ideas which are way far in the future. For example, it could make new city designs where, for example, with a click of a button, you can stop cars going into the street and then you can use it for something else. And there's some downsides to autonomous driving, which people should think about. For example, it could raise unemployment, and it could give rise to privacy issues. For example, a fleet of cars could monitor the city. So we should put these things also in mind. So what is an autonomous driving platform? So an autonomous driving platform is a normal car, but with additional sensors and computing power. So the main sensors used in an autonomous car are a camera, or here, and LiDARs, which provide depth information, and radar, which provides speed information about objects surrounding the car. And there are other sensors such as GPS, IMU, and so on. And of course, computing power. Yeah, so how do we approach self-driving? So there are basically three main ways to solve autonomous driving. And we can think in the three methods as a mapping function between the input data, which are which we get from the sensors, for example, images, LiDAR, radar, and so on. And it should provide the steering and gas commands to the car. The first approach, which is the classical modular pipeline approach, which comes from the mobile robotics navigation. And here the task is divided into subtasks which interact with each other. And these tasks include perception with its different tasks, path planning, localization, vehicle control. Yeah. Usually these subtasks are solved independently, and it requires like in lots of expertise to solve it this way. The second way is to use either imitation or reinforcement learning, where here you take a neural network that takes all the input data and you train it to give these commands. This is an easier approach. However, you cannot know what's happening inside the neural network, and at least until now, there are no guarantees for its performance. There's there's another approach which is somehow between the first two, where first you take a neural network to get intermediate representations, which is a design choice by the engineer. For example, objects around the car and so on. And you use these intermediate representations for vehicle control. So in my work, I was not focusing on reinforcement learning or imitation learning, rather on the first step of the classical or the direct perception method, where I had two tasks, which are the instance segmentation and 3D multi-object tracking. So these are my works during my PhD. So I had two works on instance segmentation, one work on implicit new representations, one on 3D multi-object tracking, and one on 6D pose estimation. I will talk about the first four works. And I will start with the first work, which is Fourier Net. Yeah, so before starting my work, let me introduce the instance segmentation task. So the instance segmentation task is you take an image and you label every pixel in the image with its class, which this task is named semantic segmentation. But at the same time, we should differentiate between different instances. For example, here, the different cars should be differentiated. However, instance segmentation is only counts for countable objects. For example, it doesn't care about trees, buildings. Trees are considered, but yeah, it considers only countable objects. Okay. So for instance segmentation methods, there are three main approaches to this. First are two-stage methods. Here you have first an object detection as a first step. And then for every box, you try to segment the background and the foreground. And to compare different methods, so we have accuracy, memory, efficiency, and the speed. Usually these are the most accurate methods, but they require a lot of memory and they're considered somehow fast. Okay, the second approach is also a two-stage method, where first we do semantic segmentation to get the labels of every pixel, and then we cluster these to get the final result. Usually these are less accurate and require less memory, but they're usually slow also because the post-processing step of the clustering, it takes a lot of computing power. And the final one is single-stage instance segmentation, which is the least accurate but most memory efficient and fast. So I had two methods in my work. One was focusing on memory efficiency and speed to make it work on a real self-driving car because of memory limitations. And the other one, I focused on accuracy. Okay. So when we are talking about single stage instance segmentation, we need to think about the mask representation of each instance. So there are four main ways to represent the mask, The first one is the grid, where every pixel is labeled either as foreground or background. Second way is to predict points in the foreground of the instance, and then we use a concave hull to get the mask. And the other one is a polygon, where the mask is represented as points and lines, and we get the mask from that polygon. And the fourth one is the implicit representation, where the mask is represented as a parameterized function, and we predict the parameters of the function to get the mask. Yeah, so because we were focusing on efficiency and speed, so we looked at literature and so which are the most compact and fastest methods. So we found a polar mask, where at each feature point they predict a number of points which would follow the boundary of the instance, like this. Yeah, this was compact compared to the grid representation, because in the grid representation, usually you would predict a grid of 28 by 28 pixels, which is too much. And here you predict just, I think, 60 points or something. Yeah, but we were thinking of a method which you predict way less coefficients or points. This method is considered a polygon representation of masks, because it has points and lines. The other one, which is explicit shape encoding, where they predict the Chebyshev polynomial coefficients, and then of the boundary of the instance, and then they use these coefficients to get the instance boundary. However, what they were doing, they were not training on the boundary itself, but they found the ground truth coefficients, and then they tried to regress these coefficients. And we saw that there's a problem in this. So for this reason, we proposed our Fourier net, which has a fully convolution architecture like the previous two works, where the image is processed through a backbone, then through a feature pyramid. And then at each pyramid level, we have a head. And in that head, at each feature point, we predict the classification of that pixel. And also we predict a centerness, which is a number telling you how much close you are to the instance center. This was found helpful with a work where they saw that predictions near the center are better. And also it predicts the coefficients of the boundary. So what I mean by the coefficients, so this is the function we used to get the boundary. So this is the boundary. Let me have this image to help you. So at each feature point, we have these axes like this, and we give the angle to the function, and at this angle, we should predict the distance to the instance boundary. And what is the network doing is it predicts these coefficients, an and bn here. And to get the boundary fast, we pad the coefficients with zeros. Then we do an inverse Fourier transform to get the contour points. Yeah, and so compared to explicit shape encoding, they were, and then we train on the contour points itself, like these contour points. Compared to explicit shape encoding, they were training directly on the function parameters, but we were training on the contour points themselves. Yeah, so, and that was the main contribution of our paper. So we did an ablation study, and we showed that if we do just coefficient regression, then we'll get very poor performance. But if we train directly on the contour points, then we'll get a big gain. And we use the Fourier representation because of the efficient fast Fourier transform implementation in PyTorch. So here, to compare to explicit shape encoding, we can see that we get smoother masks compared to explicit shape encoding. Yes. There's another thing that our mask can be really compact. For example, we can use just one parameter to represent the mask, which will always give you circles. This is maybe too extreme, but if we use two frequencies which has three coefficients, then we start to get ellipses, which is better. And as we increase the number of frequencies, we can get better and better masks until we reach a threshold where we don't increase in performance anymore. So we compared our method to all other methods which use masks with low number of parameters. So, and in this region, we always get better performance than all other methods. Yeah. So to explain this graph, this is the number of parameters used in the mask, and this is the mean average precision, which is a metric used for to evaluate object detection. And these experiments were done on MS COCO. And we can see if we use just, for example, 5 or even 8 parameters, we get quite decent results. So then we are started to looking at the limitations of our method. So for example, if we want to represent this mask, which is an instant with 2 disjoint masks, our method could not represent this mask because if we, for example, have a feature point here, then we will have a line like this, and then everything in the middle will be considered as foreground, or it will predict just this part. And it was only limited to star-shaped masks, which was also a limitation. So we said that an extension to our method is to predict the Fourier series of the level set instead of the boundary of the the instance mask. And here, like, what is the difference here? Here we're predicting the distance to the feature point, but here we're predicting like the height of the level set. And this is 1D and this is 2D. Here we have way more number of coefficients, but it has more advantages, as we will see. So now we'll talk about the second method, which is Fourier mask. So here the focus was on accuracy, and what we did here, because we are focusing on accuracy, we changed our baseline method, which is mask.
Nuri, I just need to interrupt you for a moment. Like, I see that you have 4 different subjects that you want to discuss, and maybe you haven't been informed, but we are only asking the presenters to make a presentation for 40 minutes so that we can have questions and answers and things like that. So have you like plan your talk? I don't know how long it's gonna take. Like,
Okay,
you finish your first part in almost 20 minutes. So I'm just asking.
oh, okay, maybe I will do my
Give
best.
Give us a time frame. Like, what is your time frame in general?
I was told that I have 50 minutes.
Okay, 50 minutes is fine. Yeah.
Okay. Yeah, so here it's quite simple. So we changed our backbone to a 2-stage method because it's more accurate. And instead of the mask branch in mask RCNN, we said we predict the coefficients of this 2D Fourier series. And here we can sample points depending on the position of the pixel. Yeah. So we try to compare to our previous method, which is Fourier net, and you can see here that, for example, this car, which has disjoint masks, was predicted twice, and here it was predicted once, and also here, for example, this is not a star-shaped masks, and it cannot go like this. So in Fourier mask, it was way better. The results were way better. So these are other examples. For example, here in the car, only one part was predicted, but here both parts were predicted, and also the mask quality is better. Yeah. So in our work, the main comparison was against mask RCNN, which was the baseline, and we had another advantage of this Fourier mask where we can, because like the level set is continuous, so basically we can sample even more to get higher resolution masks. For example, this is the original sampling, and if we want to do subsampling, at each step we get finer and finer masks, but at expense of speed. And we can see that our mask was better than mask RCNN, especially if we subsample more and more. So that was Fourier mask, basically. So now going to implicit new representations. So why are we talking about implicit new representation? So during our work on Fourier mask, we saw that our method was linked to the field of implicit new representations, where a neural network is used to represent images, sound, occupancy, radiance fields, and how does this work? So basically, the neural network is mapping the position of the image to its value. For example, if you give it, for example, pixel 0, 0, it should give you the color representing this position. If you give it this position, it should give you green, and so on. And this field had problems and had a high frequency problem until this work came out, which is Fourier features. And here in this work, they added a Fourier embedding to the input before the neural network. And with that, they could get high frequency details. For example, if you want to compare this image and this dragon here. And what is this Fourier embedding? It's basically taking a cosine and a sine of the input multiplied by a B vector, and then basically pass this embedding to the neural network. And in this initial work, they proposed different embeddings. Basically, the first one is a basic one, which is just taking the sine and the cosine. Then they took the positional encoding, where they have sines of and cosines with increasing frequencies on a log linear space. And they also had a Gaussian sampled frequencies, where they take a B matrix sampled from a Gaussian distribution, and then they multiply it with the input vector, and then they take the cosine and the sine. And they compared the different mappings. So no mapping is the worst, so it cannot get high frequencies. And they concluded that the Gaussian mapping was the best mapping. In our work, so we saw that if we make an integer mapping, so if we take B as an integer grid, so with this embedding, we could prove that a single perceptron is equivalent to the general form of the Fourier series. And because of that, we showed that just one perceptron is enough to represent any signal if we have enough frequencies, of course. And we also showed the connection of Fourier features to another work, which is sinusoidal networks, or sirens. We made experiments, and we showed that if we initialize the weights with the neural network, the perceptron weights with Fourier coefficients, we get the signal directly. And we also made another experiment, which is the image regression experiment. So here we have the ground truth, where we asked the neural network to learn this image. Well, actually, it's not a neural network, it's just one perceptron. And then we have different embeddings for each perceptron. So here we have siren, which has trainable frequencies. And here we have a positional encoding, which could not learn anything. Here is the integer mapping, which we called Fourier in our paper. And here is the Gauss mapping. And we can see, and here n is the number of frequencies used. We see that if we increase the number of frequencies for the perceptron, the results get better. However, for the integer mapping, we could get almost like the ground truth reconstruction image. And to put it in numbers, so to evaluate image reconstruction, we use the peak signal to noise ratio, which is a logarithmic metric. And here we're increasing the number of frequencies. We can see at the start, siren is the best because it has trainable frequencies and it can look for critical frequencies. But as we increase the number of frequencies, our embedding gets better and better. And we can see even with one perceptron, we can get really good performance. Yeah, so we had an assumption where we said, okay, if one perceptron has more representation power, does this go to multi-layer perceptron? So if we use our embedding in the multi-layer perceptron, will it have the same effect? Unfortunately, we found that the main contribution in the multi-layer perceptron setup is the network size and the standard deviation of the embed parameter values, which was the main finding of the Fourier features, and also the number of embedding parameters. We found an interesting side thing for our embedding, that it forces periodicity. So if we go outside of the image boundary and try to inference outside of the image boundary, we get the same image. But if we do it for Gaussian siren, it does not. So this is just a fun fact. Yeah. So this was our work on implicit new representations. However, Fourier mask had a second part where we used multi-layer perceptron to represent the mask. Yeah. So this is an extension of the previous table. So this is Fourier mask with just predicting the Fourier coefficients, and this is using a multi-layer perceptron where we predict the multi-layer perceptron weights. It gave slightly better results, but not too much. So yeah. Okay, so to the last part of my talk, which is about 3D multi-object tracking. Okay, so to introduce the tasks, so here we are in this task, we are required to find the 3D bounding boxes of every object on the scene, and at the same time we should track them over time. Yeah, and usually multi-object tracking has a system like this, where first it has three things. First, the detection modules, which takes the input data and gives detections. Then these are given to a tracking module. Okay, let's have it here. These detections are given to a matching module, which matches the detections with the saved tracklets in the tracking module. And the tracking module updates the tracklet parameters depending on the matching results and gives out active tracklets. In our work, we were not focusing on detection or the matching module, rather on the tracking module. So for our contributions, so we classified tracklet management systems in literature into two types. The first one is count-based. Here, the decision whether to make the tracklet active or inactive or being deleted is the number of consecutive matches, streaks, or misses, or number of misses, which was the main way for managing the tracklets. And there's another tracklet management system, which is confidence-based. And here that decision depends on the confidence of the tracklet. So it decides whether it's active or inactive or deleting it, depending on the score, not on the number of streaks and misses. And in confidence-based methods, usually there is a score update function to change the score of the tracklet depending on the matching and misses. So there was one work prior to our work which used ConfidenceBased, which was by Sun et al. And basically in their work, they were taking the matched detection score with the previous tracklet score, but subtracted by a score decay, which is something required in ConfidenceBased to get the new tracklet score. However, this led to very high scores. For example, if you have here 0.5 and here 0.5, then you have a score of 100%, and that introduced a lot of problems. So we proposed another score update functions, and we had in mind that the score should be bigger than the detection score and the tracklet score, because like if there is a match, then the system should be more confident. So we had this max function, and we had multiplication of complements. And then we had this function also. And in our ablation study, like this function gave the best results. And we compared it to count-based tracklet management system. So to explain this table, so here we are trying to see the effect of score refinement, which is using confidence-based and score update function, which I showed you in the previous slide, against count-based, which was the most used method before this. And we try to change different detectors and different filtering algorithms. So and see the effect of our change on the results. The main metrics for tracking are MOTA and AMOTA. MOTA is number of mistakes, which are false positives, false negatives, and ID switches compared to the true positives. And AMOTA takes recall into account. So it evaluates at different recall values and takes the average. And we can see that whenever we use score refinement, we get a boost. These are the results on new scenes, but this boost was consistent across different data sets. For example, also Waymo. In addition to this, we also used, in the same work, we used our confidence-based, our score refinement also in Ensemble. So here we used true tracking modules, and at each time step, we try to match between the two tracking modules and give them to the Ensemble method. And the Ensemble method tries to combine the results of these two tracking modules. Previously, there were three methods, which is affirmative, where basically put all the detections all together, and consistent, which is taking the majority, and here take just if all of the modules agree, then they take it, otherwise they don't. And in our case, we take everything, but if there is a match, the score of the matched tracklet is increased by the same functions we saw earlier. So here, shows the results on new scenes, the fusion results on new scenes. So here we show like the basic performance. So this is a LiDAR method, which gives an AMOTA of 67, and here is a camera-only method, which has 17. Here is the result of affirmative, and here are the results of consistent and anonymous. And we can see that if we use the confidence-based and confidence-based, we get better results in general. So with the two changes, doing score refinement on the tracking module itself, and then doing confidence-based on the ensemble, we got a boost of 4 AMOTA, which was a big boost at that time. We submitted our work to the New Scene Tracking Challenge last year. Yeah, I think last year. And we won the challenge with this work. Yep, so as a conclusion, so autonomous driving is a promising technology, but needs more efforts to be solved, so it's not solved yet. For our first work, training on ground truth masks using differentiable decoders was better than directly regressing the function parameters. For our second work, like 2D Fourier series level set are accurate, resolution free. And in our instance implicit new representation, we show that just one perceptron is enough to represent any signal, and it's equivalent to the general Fourier series form. And in our last work, we showed that confidence-based Tracklet Management systems are better than counter-based if we use proper score update functions. Yep, so thank you for your attention, and any questions?
Thanks, Nuri.
Yeah, welcome.
Are there any questions from the audience? Maybe I can start. In the last part, when you talked about the score refinement, can you explain the intuition behind this refinement a little better? Like, why did you come up with this refinement function? How did you come up with it?
Okay, so the main problem with, so what was used previously is the count-based. And basically, so for example, if you have a new detection, and it has had a confidence, for example, of 0.9, then this detection will not be considered as an active tracklet because it needs more streaks to be considered active. So, but we say, okay, if the detector is already confident about this, then this should be considered active directly. For example, if and with the confidence-based, like the threshold of being active or inactive depends on the score, not on the streaks. Yeah.
So this is like a post-processing thing, right? Which you can apply to any tracker.
It's not a post-processing, like inside the tracker, like you have to have this this thing, like you can either have count or confidence-based, or either direct tracking, which is even more popular now. So this is considered like the classical system more.
I was going to ask about this direct tracking. Can you think about a way of automating this, basically figuring out, like the model can figure out when to rely on detection score, when to rely on tracking score, and so on. Can you do that automatically? How would you modify the tracker to have this inherently?
Actually, we had another work after this one where we used multilayer perceptrons to basically to take the scores of the detection and the tracklet, and then decides a new score for this, and it gave a boost in performance.
Okay, it
Also,
works better if you
yeah.
learn it.
Yeah,
Okay.
with Learn it works better. Yeah, but it is slower because this is
Yeah.
basically.
Any questions from any other questions from the audience?
I have one.
Yeah.
Sorry, I had to like leave and open the door. But I don't think anybody asked this. So it's nice. Thank you for the presentation, Nuri. So how do you think this connects to like the full autonomous driving framework? You mentioned it briefly, like in your first slides, like, you know, fully designed versus fully end-to-end versus like this is there's something in between, but that was a bit more abstract. Can you give a bit more concrete examples on how this might be used? Like in what systems can you, how can you use it in, let's say, imitation learning or reinforcement learning, or how can you use it in a more designed system? What are like the broader impacts?
Okay. So for a classical pipeline approach, so first you need detection, then tracking, and then using the tracking results, you predict the future of every object surrounding the vehicle, and with those results you make a plan with the vehicle, and then you give the plan to the controller, which actually controls the vehicle. So this is for the classical pipeline approach. So if you look at the 3D multi-object tracking work, that's considered the first part of the system. For instance segmentation, usually it's used in sensor fusion. So instance segmentation results are used to project semantic information into point clouds if you're using LiDAR. And this semantic information usually improves the detection quality, which is basically the first step, and then you can continue with the classical pipeline approach. For if you're using direct perception, then usually as an intermediate representation. So let me go back to the slide. Oh, there's another way. Yeah, that depends on the design of the intermediate representation. And intermediate representations, what I have seen, usually they're trying to predict semantic information, and instance segmentation can be used to predict semantic information for the intermediate representations. Then using these intermediate representation, you can use an imitation or a reinforcement learning algorithm, which uses these intermediate representations to get the to control the vehicle, basically.
But looking forward, like what would be your bet on? What would you focus on in your, for example, next couple of years if you want to solve driving?
So I will I will focus on direct perception, basically, with an intermediate representation of computer vision tasks. For example, if it's a camera only for a system, then it's going to be depth perception, optical flow prediction, also semantic prediction. And then with these intermediate representation, then use like it would be two-step training. First, predict these computer vision tasks, and then use those to train an imitation or a reinforcement learning algorithm with those intermediate representations. That would be my way.
And can you think of a better intermediate representation than depth or semantics? For example, if you have multiple cameras, what would be a better representation in your opinion?
A better representation.
Or do you think are there a better way? Is there a
Like,
better
of course, you would like the street layout, for example. That's something that you would need. Otherwise, like, the car could go off the streets easily. What else?
map information, you mean?
Mm-hmm. Sorry?
You mean map information?
Yeah. Yeah. So.
Yeah, why not? I guess we asked too many questions. Are there any other?
Can I ask one question?
Yeah, sure.
Nuri, so I think you use level sets, right, for your boundary representations.
Yeah.
What was your motivation there exactly?
Okay. So the limitations of our previous method was the motivation for this. So here, for example, our previous method could not represent an instance like this. For example, I think it's more clear in this example. So if you want to predict the boundary of this car, then either you take the person inside this instance, or basically you predict like this part as one instance and this part as another instance. But if you use level set, then this part of the mask can be high, and then under the person it will go low, and then on the other side it would go high again. So that solves the problem of our previous method. So that.
But what property of level sets actually resolve this problem?
Sorry?
So, okay, I understand the example, but what's the deal with level sets so that we can solve this problem? So what property of level set representation addresses this problem?
Basically with the level set, you can represent any mask, but here you cannot represent all masks.
Okay, any mask meaning? Does it have something to do with topology of the mask?
Yeah, so basically with this level set, at any point it can go above the threshold, and at any point it could go below the threshold if you change this manifold.
Okay.
So because of this property, then we can represent any mask.
Okay, so as far as I know, level sets can represent any topology, right? Not only superior topology.
Yes,
So
exactly.
that's probably one of the reasons. And also you use these boundary representations in object detection to represent object masks.
Yeah.
And then do you use them also in your tracking phase? I mean, is it possible to use those boundary representations to be able to track your objects in time?
Yes.
About that, I didn't quite get that, but
Yes. So, for example, if you like in 3D, usually you can represent the shape of the object with a mask, but the problem is that to represent this, you need to have annotations for the shape of the objects. And in these data sets, like this is not feasible. So let me show you. So the only
No, my question is very simple actually. If you represent your objects in terms of these boundary representations, some coefficients, can you track them in time, or do you do that in your works, or is it something?
no, I did not do this
Okay.
in my work, and I'm not sure if it's helpful in tracking or not. If this you mean you're asking if this mask representation can be a good feature for matching two instances?
Tracking or whatever, yeah.
Yes.
Yes.
I don't know because we didn't do it, and I'm not sure if it's going to work or not.
Okay. Thank you.
Yeah, you're welcome.
Okay. If there are no questions, we can end it, I guess. Thanks a lot, Nuri.
Yeah, thank you very much for allowing me to present my work, and I hope you enjoyed the talk.
Thanks, Nuri.